All right, so Born-Haber cycle, I purposely took out all the equations on here, and I only left the names this time, kind of give you a different look. Okay? So, what I need is I want, in this case, the enthalpy of formation. And it doesn't say that, but I'm telling you now. Like, it's either lattice energy and enthalpy of formation, so the fact that I see lattice energy, that must mean that I want enthalpy of formation. And you can copy all this down straight, or else while we're writing it in, you can just put it in as we go, okay? So, here's the thing. You want to, on the top line, you want to make a formation equation. On the bottom, you got to make it from its ions in gaseous form. That's kind of the goal, okay? So, I'm going to get you started. It's lithium, and I see fluorine. It's, again, if it doesn't say everything, you got to kind of figure that out. So, it's reacting a metal, the gas, to make a salt.
How do you know that that's two?
Because it's a diatomic, hexahalogen.
Oh, yeah.
Yeah.
Oh, sorry.
No? Halogen actually means salt form, so that's also where it comes from. So now, your goal is to be able to move up and down and through all this. So what I like are arrows, and oops, I can't really move this down. And I'll give you, I'll start you off. You don't have to do it like this if you don't like it like that. And you know, I need to make lithium gas. Now if you're like, I don't like that, I'll just draw it on the side of my arrow. That's great. If you're not very neat and careful with your writing, I wouldn't do it like this anyway. Okay. I'll just do more of a line and then just write 161 on the side. Okay? So, work through it. If you want to work with someone else, you can. I want this whole thing written out, see how we do without me helping you out too much. If you need to look at some examples, that's fine, but I would try without it. That's work.
Do you have any tips on how to, or how you memorize, like what sublimation means and what disassociation and that stuff? Or not really, you just gotta use all.
I think it's a vocab word. I mean, sublime. To me, it was one of my favorite rock bands when I was in high school, so it's really easy.
So for the dissociation of that two and
Yes, sir.
it has 154 atomic. Do you do that during that step, or do you
Don't. That shouldn't be there. And I'll show you why in a minute. Thank you.
Wait, what was it?
Now, that's right, but you're not going to be given it like that. What's wrong with this top equation? Let's get to that first. I'm not done with it. Kelly? Yeah, I need to make sure, if you don't go on, if you don't make sure that that first equation is correct before you move on, you're in a lot of trouble. So, let me address Hunter's question here. So, this is dissociation. It means to separate. It might say bond energy instead. Bond energy means what energy is required to break a bond. I'm breaking the FF bond. So, your question is great, Hunter. Just unfortunately, I didn't want it to look like that. You need to understand that any coefficient prior to your value is going to affect that value. Why? Let's look at it. It says it's 154 kilojoules to break apart an F2. What am I doing? I'm breaking apart half of an F2. So I should have half the energy. That's why I said divide by 2. But I would rather have you do it like this. Okay? That shit, I didn't notice that, so good eyes. Rory says good eyes. It's like the tie I was wearing. It was a really good tie.
Did you fall for it? Oh, I don't. Clearly, that's why you fall for it. No, I didn't say. I told him I didn't fall for it. Yeah, it was fun to tie. Let's be honest. I guess that's always the question.
Let me ask you, what's on the bottom of this arrow?
Thank you.
Just F? 2F? You're breaking apart half of 2. So I'm making 1F. And just slow down on that. Literally ask yourself, like, I'll just say this, let's compare and contrast. If I'm breaking apart 2 CLs, that becomes 2 CL. right? If I'm breaking apart half of an F2, it becomes just one F.
We have to have station letters for the whole thing.
I have a feeling, I know the person who was making the test, I bet it says include all states. So then yes. If it doesn't say include all states, then no.
Wait, so you don't make the test?
No, Corey.
Wait, do you? You do it, don't you?
No. I'm not even doing this right now. I got an earpiece and someone else is telling me what to say. Hold on. No, I do. Yes, I do make it. Yes, that's right.
Most of the states are all like the bottom ones, like right after the formation equation is all gas.
The goal is to get them into gases. So if this is gas, it's already gas. This is the only one that we need to change.
Okay.
So it's not about transferring states, guys. This is about adding or taking away electrons. Okay? So this is your goal. And you don't have to write it correctly right away, but this is your goal. Now this one isn't as complicated, but now you have multiple examples. You have two on your bonding sheet. So please understand, I'm not going to give you like a second, a third, and a fourth ionization energies if they don't exist. Now they technically all exist, but not what we'd say naturally. Like lithium's second ionization energy is definitely not something that is a favorite process, because now you're dropping down to the core, right? And you're getting smaller atoms. So I can go right here now. I can go right here. Why? Because I'm one away. Jeffrey.
You need to change them both into gases.
You don't. One of them was already in gas. It's the hidden chemistry. That's just how they bond. The metal and the non-metal, the only way that they make an ionic bond is when they are both gases. And it's something that you don't think about or see. That's actually what's happening before they come together. Okay, so you write in the other numbers. Let's finish this up. Electron affinity. By the way, it's releasing energy because it's gaining another electron, so it's actually becoming smaller. Reason why it takes energy to put into removing an electron is just the way it sounds. You're removing an electron. I got to go in there. If you had like a crowbar and had to try to remove an electron, it takes effort. You don't just look at it with your crowbar and all of a sudden the door just opens up. You're like, that's what I thought. Like, yeah, so open on it with some effort. Lattice energy should always be quite large. And in this case, just so you know where they are. So, am I adding, subtracting, a little bit of both? What am I doing? Adding only, right? I suggest strongly on a test to add these columns up. So then I can directly see the mistakes if there are any. And I can also see the successes. Like, hey, they got that whole column right. I can see that with one value. Then you add them all up. Reminder, it's the creation of your cation, it's the creation of your anion, and then the amount of energy that's released when those come together. That is your enthalpy of formation. If it were different and it was lattice energy, I'd take the enthalpy of formation and subtract the cation and anion. Those are the only two things I will ask.
On the test, is it going to be, like when they give you sublimation of first ionization stuff, is it going to be in the order of which you use it? Okay.
No. The person who makes that test probably isn't that nice.
Okay. I don't like that very much.
Not many people do.
Wait.
Hello?
So like if it had a two,
Okay.
like does that go on to the first ionization level? Or would that
So you want to say there's a 2 here, let's say? For some reason, let's say there's a 2 here, then that 2 has to go here for sure. Okay?
Does it go on to the first ionization level? Does it ever do that?
Here, let me give you an example. Okay, let's say you're making, that, okay? So on the bottom, I need this. I need 2 of these, right? So then what would happen is this will make Cl, and it makes 2 of them. But here, my number is just normal. Here, I have to put a 2 in front of it now.
It's the product has 2 and 2.
No, it's not here. It's just what is ever before it. That's what you need to focus on. Eventually, it's going to match up. I'll say this. it will only be different from here to here. After that, it'll always be the same. Like the values will be the same. So it's just, are you splitting one of them by saying half of 2 is 1? Or are you splitting 2 of them making 2? Splitting 2 of them making 2. That's probably as far as it goes. Now, there could be a 3 that you need, like over here, for some reason, like AlCl3. Well, AlCl3, if I need 3 Cl's here, what do I have to have here? 3 halves, right? And that becomes 3. That's more rare.
So then we multiply that value on the.
This one would be 3 halves. This would be 3. Just the value that's the previous line. Okay? If you make a mistake on that, placing the numbers where they should go is a much more important thing. And don't underestimate that. Be like, well, knowing which process is which, that's nothing. It's a big deal. It's a bigger deal than you may want to give it credit for. We need to understand all of it. And putting it all together is not as easy of a feat as it will feel later, because you're going to start forgetting it. We're in the middle of it now, but can you continue to remember what these things are called? Because we need to be able to utilize them when we're talking about different kinds of problems. So, okay. What did we get for an answer? Negative 617. Okay. Definitely good job with the calculator. Good job. All right.
No.
Well, the questions, like all the points that got offered, all calculated.
No, this calculator's bad.
Yeah, it's a calculator.
That's what I got. We got a TI 83 plus. Same. You got that little marker there too?
Rory, that's a graph.
I've always wondered actually if you guys were like twin brothers.
I'm not surprised.
Something Rory would say.
Yeah, because I am.
Okay. What if I ask you to match these up? I gave you salts. Can you match them up? Now, I'm giving you a big help by already putting these together. Maybe I don't put them together.
Oh my God, that's not do that.
Yeah, you should not do that.
I'll talk to the guy, but again, no one likes him. I don't even like talking to him.
Just sitting in the mirror, just.
Don't do it to him.
A lot of broken mirrors at the house. I He's got his talking gloves where, you put the gloves on so you don't hurt yourself. I'm talking. Whoever's watching this right now is like, what is happening? Okay, what's the point of this?
Don't do it. Put them together.
The stronger the lattice energy, the larger the value, these are all going to be negative. So a negative value is still this is the biggest one, negative 10,000. The larger the number means the stronger the lattice energy, which means the compound is holding on to each other, that attractive force between each ion, the strongest versus the weakest. So it's based on size and it's based on charge. So we're basing it all more or less on this. So what I'd like you to do, you can either write either side. If you want to put this in order and just write them on this side, whatever. I want to rearrange these though. It's which one goes to which. And actually, I wouldn't mind I'm going to rearrange them from highest to lowest eventually. So I'm going to move them around, but you can leave them as is. I'm going to go strongest to weakest. So just actually, so what I should have done. I should have done this then. Sorry, and I'm not trying to mess up your notes. Just watch, they're already matched up. That'd be pretty funny. And done. See, guys, how easy it is. Okay, I'm gonna laugh at that. So, what are you doing first? This is what I would suggest doing. You can do either one. I like to usually find the strongest, or you can find the weakest. And what it means something different. Reminder, biggest thing here. I want largest charge, right, or smallest ion. Same thing as saying an atom for right now. So, if you want to go for the strongest first, you go for the biggest charges. If you want to find the smallest one, you look for the smallest charges. But the problem is some other ones might have also some small charges. And then you got to go to the size, so you got to kind of do both. So, anybody thoughts on the strongest one? The MG3, N2. It's the most crossing. it shouldn't really stand out. Like the ones that don't have any values underneath it, that doesn't mean there's not charges. These could be 3 plus and 3 minus. You do have to look at that. I'll say that again. It could be 3 plus and 3 minus. It could be ALN. That's a lot. It's 9. It goes in the top of Coulomb's law. But in this case, it's not. So that's my strongest one. Let's bring these down. All right. So, and if you want to give a reason, this is based on charge. All right. Now, the rest of them, it's a little harder to see, but there's still one, at least one I can do by charge that actually fits in really nicely. Which one actually is the easiest one to place right now? Let's stay on charge.
It's I98F.
Which one has the lowest of all the charges here? It's not CAS. Yep. And yeah, it's plus 1, minus 1. So that's going to be my weakest. Let's just move these guys over here. And I did this one on purpose. The reason why I'm saying that is because they all look the same. Hey. Ooh, okay. How long are you hearing? How long are you hearing? Okay, I'm in the middle of a review, but I can run down in the middle of it.
Wait, no, you were in
Okay, perfect. Okay, thank you. All right, bye.
Justin's mom.
Wait, Justin's mom?
Yeah, this is a class.
Kill
Like,
Justin.
everyone's saying, how my mom?
Dude, it's on my
We're
phone.
recording.
Honestly.
Okay. So. This has a plus and a minus 1 charge.
Wait, are you live streaming?
Yeah, he's live streaming.
So, which one goes next? Which one's the strongest one? They both. They're both 2 plus and 2 minus. So now it's about the size. So which one's going to go into the -6 in general, like generically? Well, generically, the one that has the smaller distances, the radius. So that is much smaller than these. Come on. Thanks. So they're both the same charge, but this is smaller. Between these, this is larger. Between these two. Okay? So that's how I would organize it. Fine.
Like, could you argue that the strontium, whatever, the size is like much larger than all the other ones, making it
Oh, saying forget about charge, like these are bigger?
just like.
Yeah, I hear you. Like these are the 2 biggest ones by far, SR and TE, right? Charge trumps everything because you're actually multiplying. Each time you move across, it's a matter of picometers. It's not as big of a deal as charge. Charge will dominate. Yep. Go charge first. Let size be a tiebreaker between charges. Okay, so that's how we do that one. I don't know. I don't think they turned off the. What I'd like you to do, please, is come up with, and C is a center atom, NCS, it's not a TV program. Oh, whatever.
It's not whatever.
It's not.
You were right. Figure out how many extra bonds are in that first. I'm gonna see if you can turn off this. If you're confused what I'm asking, I'm wanting this. This is the skeleton. What goes on here? So I'm looking for extra bonds.
It's a minus equation.
Or it could be a plus.
Oh, it could be a plus.
You got thing.
As a couple days, it's very plus.
Oh, whoops.
The decision is a plus or minus.
Oh no, you got a thing.
Sorry, NCS minus. Sorry. Very good to identify it. It's not a number, it's not.
Nope.
Just tell her to buzz in and then just say buzz in.
How many would this have with all single bonds? 20. So, I need 2 extra bonds, right? How many different structures can I draw? And I always try to draw the one that is the most symmetrical to start. It just kind of helps bridge. So, I gotta have at least 2. What else could I do? Sure. Is that it? And, yeah.
I mean 3, yeah, I meant 3. Well, 2 extra.
I got you. Here's a question. Which one is favored? Which one is going to be the one? So we got to use formal charts. We're going to do this together. What I would suggest is you quickly just, it's not about geometry, it's just about where they are. And yes, you have to do every single one that has not been done yet. It's not going to be more than 3. I would not pick something like 7 resonance structures. Go. That's ridiculous. But it might be 2. So, away we go. Ready, the valence electrons minus number of unpaired plus the bonds. That's 0. That one's 0. What about that one? What can I do with that one? The middle one I just did the carbon. Is that anywhere else I'm asking, I guess? Isn't that on every one of them? Oh, but it's a triple, single, double, double, single, triple. But it's all 4 bonds with no lone pairs, correct? So that means these are all zeros. I don't have to redo that one again, which is really nice. There should always be one or so that kind of repeats itself in the middle. All right. Shoot, I ran out of room on the bottom. I'll have to make room. It says 6 minus the lone electrons plus the bonds. It says -1. So what I'd like you to do right now, please do the other, at maximum 4 other ones, and see what you get. Okay? This is the only time we're doing this one today. So do the best you can. And if you're working on it, don't look up. They all should add to -1. And the reason why is that my compound is a -1 charge. They have to add up to -1 or I did something wrong. I'll say that one more time. All my formal charges need to add up to the overall charge of my molecule or I did something wrong. It's a big deal. So, you said there, which one can I get rid of? Like, it's gone. 1, 2, or 3, let's call it. Y3. It's at 2. The goal is 0. The goal is 0. So the further you get away from 0, the worse that is. Okay, so now you have a decision. And keep it straight. I have 0 on an N and -1 on an S, or I have a -1 on an N and a 0 on an S. How do I make that decision? Hunter.
I don't know.
That's all right.
Electro.
Yeah.
Go ahead. I don't know.
Electronegativity, okay. Well said. Keep going. Well, you can't just say word, you gotta tell me. I can say unicorn and it's really beautiful. Go.
S is more electronegative than N, so it would have to have
If there's a tie, and a few of these you gotta look up and be like, wait, actually it's not. Based on just this, I'm just telling you, like, if there's a top, like some of these that are lower actually are the same values, even though they're more to the right. We're just basing it off of just trend. S is more to the upper right, so we're going to say that S is the more electronegative. So that has to be, I'm sorry, you said it, but has to be the what? So S is more electronegative, so how does that apply? Negative value, right? Question, Jen.
Why can press that on?
Because I had a 2. It's even further away from 0. Like, you're trying to get as close to 0 as possible. When you start getting 2s and 3s, that means that those atoms are really sharing or giving away the electrons more than what is a normal energetic approach to their bonding.
So the most electronegative one has to be the
Negative. Because what it means, if you want to interpret it in a way, even though formal charges aren't really real, is that if it's negative, it's taking more electrons onto itself. And if it's positive, it's actually losing electrons to something else, while electronegativity is about who can pull electrons towards itself. So that'd be that. Right?
How would you phrase that question? Like once you make the resonance structures?
I would just say which structure is most favored using formal charges. And if I ask for a simple explanation, what I would say is this structure, I have an arrow and say this structure is closest to 0 with the most electronegative atom having a negative formal charge. Done. Okay. Okay. Moving on. This is what I want. Give you a hint. N is the central atom. Okay? The second one. N is a central atom. Go. Work these out. I'm going to be right back. I gotta go get a couple of deliveries.
You don't trust us?
Yeah, there is. There's 2 more pairs.
Okay. I'm going to start it.
Oh, I thought you meant something kind of like
So, you guys, if you're not sure how to do this, on the side you need to think about what's happening. So I got 4 CLs, or sorry, 4 Fs onto the CL, so that would create 32. That's my T. You're like, I don't know why I do TV all the time. I don't get it. The reason why you're doing it is to figure out if you need extra bonds or if you need extra lone pairs. Like, what's the number of clouds in my central atom? So this is 7 plus another 28 plus another 1. So that's 36. Right? So difference of -4. Don't sit there also memorizing all that. My picture, which is T, is short by 4 electrons, which is V. So I think, oh, that's 6 clouds. The mechanism should go off. Oh, 6. That's the vertical axis with a square. I put my lone pairs across from each other,
Oh yeah.
and I make my structure. Layla.
So on the test,
So then you're making a tetrahedral.
Well, no, I mean,
Oh.
you put like the multi-pairs on there, but you didn't put them in that slot. Would you get points off?
Where did you put them?
Like if you put them, oh, I did it like that, but I'm.
They need to be across from each other. They need to be here and here, here, and here.
Well, I'm just saying.
On
Like,
a trigonal pyramidal,
yeah, something like.
if they're not on these three, then that's wrong. Because that takes up more space in there. And lone pairs take up more space because they're not bound between two atoms. Okay? Sigrid?
Yeah, so if you just asked for something like that on the test and we didn't make it, like it has to be 3D.
You know, pretty?
Yeah.
It will actually say 3D drawing, so yes. Yeah, you need to give it a little extra. If not, it's not here. You're not gonna not get into Yale or anything for it.
We have to put the brackets around it for the 3D drawing.
Right. Oh crap. Why is that a
He
no?
knows what he's talking right here.
Because, thank you, Logan. Wasn't done.
I forgot about that.
Because you have a charge, you do have to put a bracket. Because you're saying that that structure, if you don't put a bracket and tell me what the charge is, that's actually short an electron. You're one electron short. Oh, the secretary made a good point. She didn't actually ding me through the ceiling. She called me. Like, I didn't.
Wait, so I still reading.
It's the whole school. Parent geometry. Yeah, they're building a new one now. Octahedral. It's a square. And it's flat, so it's in a plane. Hybrid, it's based on clouds, not based on bonds. So I have 6 clouds, so I say S, P, P, P. There's no more P's, so then I start going to D's. This is an SP3, D2. Bond angles, these are 90 degrees. If you want to write 180, that's fine, but this is 90 degrees right here. They're all 90 degrees. And last one, polarity. Is it polar or non-polar? Non-polar. I did 2 different ones. One that was a little more toned down. This one, I just drew it out quickly here. That would have 20. How many should I have? 16. What? Well, that means that, yeah. But if I'm not asking for a resonance structure, then you gotta just write it out the way that it is. So I'm gonna have 2 extra bonds. So no, like if it would probably be something that would make you have 2. It would just be pretty clear where it's gonna go. So then, in this case, there's nothing else on the center atom. So this is linear. Yes, I could ask for linear on an AP exam. Like, it could be linear. It's not like, oh, you wouldn't go that easy. Why not? Sometimes the easiest ones are the most difficult ones. There's no lone pairs in the middle, so the shape and the molecular shape and the parent geometry are the same. Hybrid, 2 clouds, SP, bond angle, 180. Is this polar or non-polar? Polar, because it's not all the same. That being said, I'm going to use this one right here. So, stem off from this, please, and I want to talk about 2 different bonds. I want to talk about each of these, just so you see the differences and the similarities. Actually, I probably could just talk about one, honestly. But we'll do one other one then after this. Not that you need them there, but the single bonds are sigma bonds. Sigma bonds are hybridized, meaning that you're using S's and P's. They both, I hope you agree, and if you don't, we'll hopefully get there, is that they each have a sigma and a pi. The first bond's always sigma. There's no such thing as 0 sigma. So you have 1 sigma at least, and only, actually no, there's only 1 sigma. It takes up that space in the middle, and the pi bonds have to reach above and below. So the nitrogen has this nitrogen has an SP. There's 2 clouds, SP. Notice I'm writing it underneath. I'm trying to do it in the orientation of my structure right now. What's the hybridization of that end?
Which SP2?
The one I'm pointing at, SP2. And then this oxygen is also SP2, right? Because there's 3 clouds. Wait, where? 1, 2, 3. What's the pi bond? It goes off of, and we'll do one that will challenge it a little bit more. goes off of p orbitals because they have to reach above and below. They actually literally have to go off above and reach. That's what that other bond is, and you have to draw that. But so this end, there's nothing I can say differently, but there's something we need to talk about. And this is also both two p's. Why? They're all found on the second level, but this is specific because it's in the same structure. So what do I need to do?
Put Z's in X.
Yes, so what can I put here? Let's do X. Then what that means is, I'll just do this in red, this one's like in a different plane. How am I supposed to know which plane is which? Just so you don't mix them up and have them the same. That's all you need. So you can make it whatever you want. I'm going to do a Y. If you want to do a Z, that's fine. Just don't mimic an X. And don't make a Y and an X being bonded together. They don't bond in different planes.
Why is it only SP? Never mind.
Sure.
Yeah.
Okay. So let's do.
Oh crap.
Okay.
Oh shit.
Mr. Gussie, are you recording this right now?
Mr. Bench, are you recording?
Wait, what? Mr. Valence, are you recording today?
Now I'm nervous.
He doesn't record these.
All right, last one here. Let's talk about these three. Actually, let's make that an S. I'm going to make that an S on the top. This is my last one of this, and then we have one more problem to do, and we're done. Which we're about. We're a good time. So I want to talk about each bond. What if I ask, explain the orbitals involved in each bond? So I have the HC, I have my C double bonded S, and I have C double C bonded to Cl. So H's cannot hybridize. To hybridize, you need actually two different sublevels or orbitals to even be a hybrid, because the hybrid is a combination of two things. So I have one S. This is a single bond. So I have to look at the overall hybridization. And don't look up. I may not say anything. I may just say, provide all the orbitals that are involved in the bonding. Here, you need to recognize you need to give me two. Oh. So I have a sigma and I have a pi. Sigma, sp2. What's the S? Yeah, it's not uncommon to have the same hybridized orbitals. But what's the pi bond? Pi bond again deals with the p's, so please fill that in once. You don't need a subscript, it doesn't hurt to have one. One-ish.
You just kind of put whatever you want on there?
Sure. Jeffrey.
You only need a subscript when like there's multiple pi bonds within one structure, or like one.
Within one pair or one structure, like this one was in separate ones, then you should. Because then you're declaring that they're in different ones. But like this one's the only extra bond, so it's not as important.
Oh.
Yep. See, okay, so carbon is on the second row, so the electron that's bonding that is actually like sitting in a 2p sublevel. The electron that's bonding with S is in the third energy level, so that's why it's a 3p. Okay? And then lastly, It's still hybridized, so you say sp2, and then this one is 1, 2, 3, 4, and I'm going to take two different answers on this. It can be sp3, or the packet that we've been working on has basically been stating if it's not the central atom, then you're not hybridizing those because those are not contributing to those angles, which still have, it's hard for me to put my head around that one because the electrons are still going to get as far away as possible. So what else could I write if I'm going to say it's not hybridized because it's not a center atom? 2p? Look where it's located. Mm-hmm. There you go. Either one works. So we're going to finish up. It would be a lot easier if you have it. Yeah, your little bonding energy sheets, your little half ones. Last problem. It's a short one. You mean a subscript? No, only on double bonds and things. So like, oh, no, this is a single bond, so it's in the plane of the board. I'm not saying this is a difficult one. I'm not saying this is an easy one, but for the sake of review, I'm trying to just apply it to what we need. So what I'd like you to do, I'm going to give you a couple minutes, about 3 or 4 minutes, try to figure this all out. I'd suggest writing the formulas on the bottom before you get there. So you've had a little time to work on it. I'm not going to do all the work yet, but you can double check a couple things. You need that, one way or the other. So, you need to have the products and the reactants straight in your mind. This is not products minus reactants. You are breaking bonds and then you are making bonds. Okay? So hopefully you were thinking more like this. Do I subtract or do I add them? Subtract. And the reason why... Sorry, thank you.
I didn't.
Two of them, which I think it's important to do it in red here, because your brain doesn't move up there. Thank you. Do I subtract or do I add them? You said subtract. Why? Because when I make a bond, it releases energy. So that's what that negative is discussing there. By showing just there, I was doing that, and you're like, no, you missed something. If you just write out the numbers right away, you won't see it the same way. You got to write that out. That's showing all the work. That's showing all the relationships of all the bonds. Rory.
Is CH, is that the same as HC?
Yes, sir.
Correct.
So then you put in all the numbers. I'm not going to do that. You can do that. You factor in the two. I'd suggest having two values then, this value minus the other bracketed value, and then you have an equals at the end. Logan, what did you get? Did you get an answer?
158.
Negative 158?
Yep.
Negative 158, anybody else? Just confirm?
I got
Okay.
it.
All right, I believe we've covered everything on the test. I'm hoping you're feeling like you got it, like maybe you're heading in the direction that you need to. If you have any other questions or need things clarified, I will stay after to talk about it as I transfer this.